All right, didn't get any questions asked in advance. Lost on there. Questions asked in advance for live stream today. Again, these are lessons. These aren't lessons or lectures. These are office hours. Now, did notice there's a little confusion. The oral reports I'm referring to, they're for 152. They're not for 251, 252. In 2 weeks, 152 is giving their oral presentations. We push it back a week because generally that 2 weeks is allocated because there's 16 students. It's 8 per week. Kind of keeps the load down for seeing through that many presentations. We're just going to push it back, and next week is a review session, so show up with your questions. So yeah, show up to your questions next week. That's the big questions. We are in the last 40% of the semester, so I'm getting here towards the end. So if you got questions about the rest of the semester, please feel free to ask them. Otherwise, I'm going to be here kind of getting work done. All right, got a question about slide 12 on the PowerPoints. And in this slide, we have this reaction of cyclopentanone with water. So we got H plus. Actually, we're specifically looking at deuterium, DTO. So there's two reactions to consider here. One is a non-productive reaction. It does go on, but it's not really the point we're getting at here. And this is where the water adds across the ketone to give our arginal diol. So this does happen, but it's not a particularly interesting reaction, and it's easily, generally speaking, it's going to lie more towards the ketone than it is towards the diol, but it does occur. The more interesting one here is that, so water is composed of two things. It's composed of H plus and OH minus, and here instead of hydrogen we've got deuterium. So what's going to happen with the deuterium is that deuterium is, or this deuterated hydroxide, is going to abstract the hydrogen off of our ketone. And it's a short-lived compound, but it does exist. And it's this weird HDO plus D plus. Let's make sure you can still see that on the screen. Sort of. So the first thing we're going to generate is this anion, and this isn't going to end up being resonance stabilized. So we can kick down and we can get this enolate ion. So because of this resonance stability, this anion is actually stable. It actually is produced in trace quantities. But it does go back and forth. And in the process of doing so, if we have a deuterated solvent like H2O, what's going to happen is that statistically it's more likely that it's going to grab a deuterium than a hydrogen. So let me kind of rewrite this so it's more centered on the board here. So we've got our deuterated water splitting into two parts. It's going to abstract the hydrogen, and we're going to get this resonance stabilized carbanion with HDO. So we have it's H2O, but we've got a deuterium ion. And again, it's resonance stabilized to give us this. And then our deuterium plus here can be attacked by the carbanion, and we end up getting, again, the reversibility errors on all of this. We end up beginning to replace the hydrogen with deuteriums, and we can keep doing this. If we have a sufficiently large quantity of water, the statistical likelihood that it's going to pull the hydrogen back off is really low. And so as this reaction carries on, we're going to swap out more and more hydrogens with deuteriums until we ultimately replace them. Now, the deuterium here is not the important reaction. It's more to illustrate that, yes, we can actually measure this. We can, over time, plot the NMR and watch as the deuterium exchanges with the hydrogens, but this tells us that this does happen. And so we do, because of ketones and this resonance stability with the enolate ion, these are actually very acidic hydrogens. So if you compare it to something like cyclopentane, this isn't going to do anything with water. We're not exchanging any hydrogens. But particularly with this cyclopentanone, we're getting substitution, we get acidity, and we get high acidity here at the carbon position. Now when I say high acidity, we're not talking about like carboxylic acids. But it's enough that the water can actually exchange ions with it. And so this indicates to us that one, these are acidic hydrogens, and two, we had the ability to generate an anion, which means that we could start undergoing reactions. And this is something that you did with the aldol condensation reactions when you did them in the lab, is that you used a strong base here to pull off that hydrogen and generate an anion so it would react like an anion. Congratulations for having your cat slightly healthier than usual. So the D isn't really removing the hydrogens, it's swapping out with it. And so what you're actually seeing is an acid-base reaction. So a parallel here is carboxylic acids. So we know the hydrogens on carboxylic acids are acidic, that's why they're called acids. And let's say it was in deuterated water. So we can have the hydrogen, we can have the, it's an acid, it'll pop off. And we end up getting the D2O plus, the deuterated version of the hydronium. Now, when the carboxylic ion takes the hydrogen back, because this is a reversible reaction, there's a 1 in 2 and 3 odds that it's actually going to grab the deuterium back instead of the hydrogen, all things being equal. Now, if we have a lot of deuterated water, D2O, this gets astronomically small. But instead of forming this, we can also form OD, DHO. And so, by sheer merit of the fact that that hydrogen is labile, it can come off, it does exchange with hydrogens that are in water, which are also acidic and labile. So the deuterium labeling is not a particularly interesting reaction. The book claims it is. I haven't really seen a lot of people that care about it. That's not what's useful about it. What's useful about it is that it demonstrates that those hydrogens on a alpha carbon, one that's adjacent to that ketone, are actually acidic. And this is not what you'd expect for an alkane. For these carbon-hydrogen bonds, are typically very strong bonds. They're hard to break. That's why we need something aggressive as free radical halogenation or combustion to break them. But in this case, not only are they labile enough to exchange with water, which has a pH of 7, not particularly acidic, we know it goes through a carbanion intermediate, which means that we can exploit this. We know that occasionally, so carboxylates we know occasionally will look like this. They have that negative charge, and that negative charge is a Lewis base that can attack vulnerable carbonyl carbons. In this case, we end up kind of unexpectedly getting 2 carbon positions that are actually carbanions, very temporarily, but they're long enough that they can undergo Lewis base reactions, particularly on carbonyls. So if we have something like an aldehyde, there will be a short-lived moment where this is an anion. This anion is going to attack the carbonyl, and once we form this carbon-carbon bond, the carbon-carbon bonds can't be undone. And so we can end up, just by using bases to abstract those hydrogens, make carbon coupling reactions. And again, you've done this with the lab. This is the addition. This is the basis of Aldol addition. And then ultimately, Aldol elimination will follow, where we're able to end up getting these double bonds if we can do it. So again, D isn't removing hydrogens, it's just replacing with it. Because D is hydrogen, it's just isotopically labeled hydrogen. The hard part for this unit is the aldol condensation, Michelson, Michael reaction, Robinson emulation reactions. And the hard part here comes about from 2 points. One, any alpha carbon adjacent to a ketone can form a carbanion. So let's say you had excess of this. Well, now both of these are going to form these aldol condensates. So you have to keep track of both carbons, and they can definitely react unless we keep the stoichiometry down. The second issue is that they can react with themselves, and this is going to be a very common thing, particularly with the Robinson emulation and the Michael reaction. We're going to end up making 6-membered rings, because 6-membered rings are inherently more stable. And you'll see this in the notes. With the Michael reaction, we're going to draw our cyclohexene ring, or specifically the alpha-beta unsaturated. And yes, I know that's a lot. But pretty much with all Michael reactions, you're going to end up generating this as a component of the molecule. So this is going to show up somewhere in there, and it's a self-reaction. The Robinson emulation and the decarboxylation are like things that can happen, but again, the big one, the Michael reaction is this. Rather than elimination, it should just go for ring expansion, shouldn't it? Actually, so the elimination, the removal of the water, the driving force here is conjugation. So even though this isn't carbon-carbon, it's carbon oxygen, these are still conjugated. So the elimination is the big thing, but yes, for ring expansion, this is a big thing that drives the Michael reaction. We end up generating a lot of 6-membered rings. Very easy to do. Because we can do it, it's going to happen a lot. But really, that's the hard part. And this is why, this is technically still reactions of ketones and aldehydes. That was the previous unit. But this is why I split it up, is that this kind of goes to the extreme of reactions of aldehydes and ketones. Now, with the amine chemistry, the amine chemistry, the bigger thing are the azide, azo reactions. Azo coupling is a huge component. It is the foundation of azo dyes. It is a huge field. We're only going to touch on it, even though there's a lot of it in the textbook or the notes, we're definitely only going to touch on a very small part of it. Reactions of phenol, hopefully you look at that and go, oh, it's benzene reactions, but this time instead of starting with benzene, we're starting with phenol. And that's kind of the better way to approach it. There's only one unique reaction. It's the Kolbe-Schmidt reaction. It's a way of basically making salicylic acid. It's a cool reaction. Not gonna lie, it's kind of a cool reaction. But that's really the only thing with phenol that's anything radically different than we've covered. So I've tried to take the fourth unit and make only one big hard concept in there. Again, I realize with amines, azo coupling can be a little overwhelming because they do so much. But honestly, with amines, they're predominantly going to do SN2 elimination, so SN2 reactions. We will get Hoffman elimination. This is actually a question you asked earlier about in the semester, was Hoffman elimination. Hoffman elimination is going to come up here. Hoffman elimination is just like basically the anti-Zaitsev's equivalent of elimination, but we're going to keep it simple. And that's kind of going to be the theme with amines. We're going to keep them simple. I'm sure there's a lot of complicated stuff with them. The big issue with amines is like to form, what are they called? Ammonium salts. And this is a big reason why we kind of stay away from them, is that while they are nice in terms of the chemistries they can do, they also do a lot of unwanted side chemistries that we're not interested in. So the salts, an example of this is you have like tetramethyl ammonium iodide. It likes to do this a lot. But yeah, the microreaction, hopefully the notes help you out. I find it easier to go backwards with the microreaction than to go forward. So instead of like looking at the molecule and saying, oh, okay, this will do this, this will do this, it's kind of like Diels-Alder. I like to start with a base molecule and say, okay, based on what I should end up with, where should everything attach? Because Diels-Alder, you can kind of like do a forward prediction and say like, oh, this will combine with this should get this. I prefer the reverse engineering with starting with the cyclohexene and going backwards and saying, okay, well, the cyclohexene was made, where did these different components attach to it? And I will give you the full disclosure for the exam. Microreaction will be on there. We're going to keep it really simple. So unfortunately, because we're keeping the test simple, it means the packets inherently are going to have harder questions on them because of the limited test pool. But again, we're not going to like the extreme of super big molecules. Say with the discussion board is probably good. The discussion board for aldol condensation is going to be a lot more complicated than the actual exam. Ask your question about the aldol. Yes, go for it. Yeah, hopefully you're seeing in the slides, like, aldol condensation quickly gets super complicated. And yeah, we're going to keep it simple. Yeah, hopefully you appreciate slide 81. Yes, so the way the lab was run, and this is just more of a practicality of it, you're looking at this reaction. So we got two of these, and ultimately what we want to produce is this condensate. The problem is that this can self-react to give, so if you have two of these, this can self-react to give this compound here, especially if you got three of them. So when we start at the lab, we keep this concentration really low and this concentration high, and this ensures that if anything, we get the first condensation product, and then we start adding more to kind of, well, okay, so we keep this low in hopes that we drive pretty much all of this reaction, and then add this again. So this just starts as the limiting reagent just to ensure that it's selective for this. And this ends up becoming the excess reagent when the lab is finished, so that this becomes the limiting reagent. I mean, you can always post the advanced questions. We can see if we can answer them. I think organic's a little too advanced for high school or 12th for grade school. I understand all programs are different, but it's like this is kind of like organic is considered a specialty in chemistry. So for chem majors, this is the first specialty course they take. And so I understand teaching Gen Chem because Gen Chem applies to everything, but organic seems kind of like an esoteric, like just arbitrarily hard to keep your GPA down kind of question. No, slide 1 is this, ask you to name this compound here. So for slide 81, so this is the example given. It says amines, amides with multiple functionalities, and the bullets are as follows. No, or just no, we're not doing this. Bullet 2, the naming as far as I can tell just falls apart with trade names, common names, brand names, and everything else falling into the mix. Bullet 3, we have a tool for dealing with this. In fact, we have several, and in terms of most useful to least useful, they are 1, Google. 2, NIST Chemistry Webbook. 3, Spectral Database of Organic Compounds, SDBS. 4, your textbook. 5, your fellow chemistry student. 6, a college chemistry professor. 7, a college professor. 8, some random person you meet on the street. So, we're not doing, when it comes to amines, we're pretty much just doing alkyl functionalities. So you have like alkyl amine, NN alkyl alkyl amine, or N alkyl alkyl amine, and NN alkyl 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 amine. We are not delving into super complicated functionalities. There is simply no point in doing that. Yes, for the lab, you do need to include the reactions. I would recommend, if you don't have it already, ACD ChemDraw. That is a freeware ChemDraw. It doesn't play very well with Mac, but if you have a PC, it's a nice freeware program. There are little nuances. One nice trick is F8. F8, so if you hit function F8 on your keyboard, it will clean up the structure. Sometimes it makes mistakes, but generally speaking, it's pretty good about taking like alkenes in particular and making them look really nice. Yeah, if you ever look at the Wikipedia stub on like IUPAC naming, like they're full, the mother of all IUPAC, it's like 20 pages just establishing what's the primary functional group. And you can try to follow the rules, but yeah, you're welcome. You're going to quickly find, following the IUPAC rules, they start contradicting each other. And it's by sheer merit of the fact that no matter what combination you come up with, there's always one more combination. There's always one more complication. So it's like trying to create a word. It's trying to create a letter for every word in the alphabet in the English language. No matter how many words you represent by symbols, you ultimately have one more word that gets generated. Same thing's true with IUPAC rules. For every rule we create, a new functional class is created, and so now you have to come up with new rules, and you have to figure out where the new rules fit in the pantheon of the old rules. And it's just too overwhelming to really be bothered with. So IUPAC works for very simple, and I'm not disparaging IUPAC. IUPAC was a great idea. I'm glad we did it, but it's also kind of nice to see that you're blossoming in your chemistry careers and beginning to see that you're definitely going to hit a point where it just doesn't work anymore. if there wasn't a mixture of stereoisomers, how exactly would that appear? Would it be visible to differentiate between having less or more? So technically, so you definitely generated a mix of stereoisomers. You probably also generated the aldol. So there's a lot. Okay, so let's start with just the Aldol Addition product. So that's a chiral OH, and that's a chiral OH. And there are going to be R and S versions, and one of them is meso. So there's three possibilities here. Now, if we do the single elimination, we have an R and S combination here, and we have an E and Z combination here. So now there's four possibilities. And with the aldol condensate, we have, even though we've written it as trans, we have the EZ and we have the EZ. So there's three possibilities here, both E, both Z, one E, one Z. So in total, there are 10 possible combinations you could have extracted from this aldol condensation reaction. So you probably noticed with the aldol condensation reaction, in fact, I comment in the notes, there are cis-trans possibilities, there are RS possibilities. We do not name them, and we do not draw them in for that matter. So we're always going to draw the trans product, even though the cis product is present, because the trans is most likely to exist. With the alcohols, we're going to use relative configurations. We're not going to bother to label R and S and say it's probably a racemic mixture of both. The reason being is that up here with a very simple aldol condensate, your benzaldehyde and acetone, you made 10 different stereoisomers. Now, are some more likely than others? Yes, you probably have the EE form of the condensate as your particular large component. The way you would figure out the ratio, and you kind of saw this with the TLC, when you ran the TLC of your product, you roughly got 4 products. You probably got this, this, and this in different ratios. And so the TLC would give you a qualitative estimate of the different combinations, but it wouldn't tell you which one you have. So what you do is optimize the mixture with TLC to figure out like what's the best way to separate it. And then you would have to take a column chromatography, use column chromatography to separate out the different bands that you see in the TLC and subject them probably to both infrared spectroscopy to figure out which ones are condensates versus addition products, and then subject them to polarimetry to figure out which ones you have, like R and S, things like that. Now, chromatography typically can't resolve chirality. So R and S versions, not only would you have to do chromatography, you'd have to do chromatography across a chiral column. So you need specialized silica gel that has like all R or all S. The less spots in Disney would just show less stereoisomers. Yep, pretty much. So if you had one big band and little ones, you could say, well, I've got a majority of something. Now, what that something is, that's kind of up to debate. That yellow color you saw when I ran the TLC, that's actually like not the top band. The top band was the majority product in the TLC I ran, which I think was actually your product. And so I don't know what the yellow is. My guess is the yellow is this one, since that would make sense for conjugated compounds typically are what are called chromophores, so they have a color to them. Your big product may have been this, since alcohols typically aren't chromophores, but I may be wrong. This may be the chromophore that was clear. But we simply don't have the technology at Wake Tech. I mean, we do have the polarimeter, but we don't have this. And I mean, it's cool. Like, this is good real-world chemistry for you to be exposed to. But that's why I said in the lab, like, you're free to speculate in this lab report and say, like, okay, I measured the product. There is good reason to think it's these. But for all you know, it's really the aldol condensate of the acetone with itself. That when you add at the base, you ended up generating whatever the acetone equivalent of the aldol condensate was. Again, we would need to run column chromatography. That is absolutely positively not worth it. And I say that as an instructor because these are all clear compounds. You're not going to know when they come off the column, so you would have to collect. What you do in practice is that you collect it all as it comes off the column, And so you run your ethyl acetate hexane mixture, and then you collect a milliliter, collect another milliliter, collect another milliliter, and you analyze all the milliliters you collect to identify which ones contain your product. I think that's useful to know, but I think in terms of an undergraduate organic chemistry lab, that is way too much work. We are looking on a column chromatography lab for organic too. Big limitation right now is we need to free up time in the schedule. That'll happen if we get a drying oven. That's down the road, down the road kind of story. But we have agreed as instructors that if we do make you go column chromatography, they're going to be colored bands, so you don't have to sit there and collect little milliliter aliquots and figure out if your product's in it. I know that was a long answer to your question, but I want to make sure, like, practically, yes, you would go through and try to figure this out. Honestly, I would love to get what's called a drift setup, diffuse reflectance infrared spectroscopy. So you could actually measure IR of your individual spots on the plates themselves. Drift measurements are a bit more complicated. I'm not going to really get into that. I think the theory is like way too much to worry with in a live stream. But ideally with the drifts, what you could do is you could label your TLC plate and slide it across the drifts detector and figure out what each spot is. It'd be something cool to do down the road if we ever get an IR. But I do wonder, like, particularly for the ones that like moved really far up the column, if they weren't some iteration of the acetone with itself. That's a possibility. I don't think it's a likely possibility, but it's a possibility. Actually, I should try that with a bottle. Just get a bottle of acetone and chunk some sodium hydroxide in it and see if it forms a solid. Something to play with tomorrow. Okay, so for aldol addition condensates, ketones are the hardest ones to work with, and so we're going to try to stick to basically ketones with themselves and definitely try to stick to symmetric ones. Aldehydes typically do not attack ketones. It's the other way. Ketones like to attack alcohols. This has to do with the stability of the relative enol, not really predicted by Lewis theory. But let's start easy with a symmetric ketone with itself. So with the symmetric ketone, our acidic carbons are the ones that are adjacent to the carbonyl. So if we're going to attack, it's going to be that carbon to the carbonyl. So where are my other things? Glue would be okay. Hopefully you can, shit's red. So the ketone that does the attacking is going to come from the alpha carbon. It's going to attack the carbonyl. And the reason being here is that we're making, when we use a base for this, this ends up becoming a carbanion. That's your negative, that's your positive. So we're going to get an attack there. And what I'm going to do is I'm just going to draw the ketone upside down. So when we get the attack from there to there, it's going to kick that bond up, and we'll end up getting an alkoxide. Sorry, that's kind of in the glare of the light. So again, I got my starting ketone. And this is my acidic carbon. It's going to be a carbanion. It's going to attack the carbonyl carbon. push that carbonyl carbon up. So that's this red carbon here. And this is your addition product when we acidify it back up. So this is how you generate the alcohol. Now, if you had excess, it would do the same thing from this carbon. Reverse. So these are the same ketones. So you could do it from, this is what I'm going to say, we're going to stick to symmetric ketones if we can. So this ketone and this ketone are the same thing, and we'll talk about asymmetric next. Asymmetric is just harder from just by sheer merit of different combinations. So your condensation comes when this OH comes off and this hydrogen comes off, and you just end up forming a double bond here. So that's your aldol addition, where you form the OH, and the condensate is when it eliminates. What happens if they're asymmetric? So let's call this ketone A and ketone B. And again, we're going to stick to symmetric ketones. Definitely if it's asymmetric, you're just going to add another layer of complexity. You can do it, it's just another layer of complexity. So there's two scenarios. A attacking B, B attacking A. So if A attacks B, again, I'm just going to flip this one upside down. One of the alpha carbons here is going to attack the carbonyl. So we're going to attack from here to here. This will produce the alcohol on acidification, and if we do elimination, we'll get the alkene. If we have B attacking A, I'm just going to draw A upside down. We've got the alpha carbon, which will attack the ketone, produce the alcohol, and if we do elimination, we get the double bond bound. So if we have two different ketones attacking each other, why is elimination going on? Why does it occur, and how would it be favorable? So we finish this thought first. So if we have two different but symmetric ketones, we would end up generating two products. One where A attacks B, one where B attacks A. Now, the driving force for elimination here is conjugation. We have a pi bond here and a pi bond here. It's just like carbon-carbon pi bonds. When they start doing these pi bonds, they start associating with each other. It ends up being more stable. So this is the driving force for elimination. Now, two ways you won't get elimination. One, you run it in absolutely neutral conditions. Not likely. Option two, this one doesn't have two hydrogens on it. So if I run this reaction, so I have, so now this is A, I've still got B. When this attacks, in order for this OH to pop off, there has to be a hydrogen up here to eliminate, so there isn't a hydrogen to eliminate. So if your alpha carbon here is tertiary, it won't do elimination, and you'll be stuck with the aldol condensate. But that said, if you do have two hydrogens or more on your alpha carbon, so I can take the same one, turn it upside down. This can attack, and then because we have a hydrogen here, it can do elimination. We'll end up getting this. So what happens if we have asymmetric and two different? So we'll just make A asymmetric. So for A being asymmetric, we have A attacking B, but we've got carbon 1, we've got carbon 2. They have a different number of hydrogens. So I'd have to consider two possibilities. A, where the first carbon attacks B, and A, where the second carbon attacks B. So if the first carbon attacks, again, I'm going to draw B upside down. And here we'll just do the aldol addition. We won't worry about the condensation. This carbon will attack this carbonyl, and will end up forming the alcohol. So this acidic carbon will attack. For the second carbon attacking, this will attack and form the alcohol. Here we can only get the addition product. Here we can get the addition and the condensation product because of the alpha hydrogens. Now, if B attacks A, we don't really have an issue. So that carbon will attack, break, we'll get the aldol addition product, and it can further do the condensation. Now, what if both A and B are different and they're both asymmetric? So if they're both different and they're both asymmetric, we would have we'd have B attacking A, but we'd have to consider the two different carbons. So the first carbon attacking A and the second carbon attacking A. And you would kind of get this like tree diagram where you had to consider every combination of alpha carbon attacking the other ketone. This is what I mean. This quickly becomes super complicated problems, and we're going to stick to very simple ones. Now, a nice thing about this is that aldehydes do not attack ketones. Ketones attack aldehydes. So if B was just an aldehyde, we don't have to consider this case. We only have to consider the case where the ketone attacks the aldehyde, but not the other way around. It's a really nice simplified version. What it has to do with is that aldehydes are simply more reactive than ketones. So while, yeah, there probably is some B attacking A, a majority of the reaction is going to be A attacking B. Now, this also assumes that you only have a single attack of a ketone on an aldehyde. So let's go back to symmetric. Let's go back to the symmetric ketone attacking itself. So the first reaction here would generate this condensate. So I guess I should write it out for you. So if we have this ketone attacking this ketone, and now it attacks, and it generates an OH group, and we've got the aldol addition reaction, there's nothing to stop the other carbon from attacking. So we have this carbon, and this carbon is still acidic. So now we can react it with itself again. And this can attack and form the other aldol addition reaction. Consequently, if we had, because this is now in the mix, this could attack itself. And you can get a lot of self-reactions with these types of condensates. So there's a lot of control here concerning like concentrations to ensure that you get the selectivity you want. So even with a symmetric ketone attacking itself, we're only going to consider the first reaction, the self-reaction. We're going to treat it like we're keeping it in low concentrations. But there is nothing stopping this product from turning around and using its alpha carbon to attack one of the others. And there's also nothing stopping this from attacking itself. And we can end up like you can see that power of 2 start showing up. Like you can get 2, 4, 6, 8 to all types of products depending on the different combinations you work with. Again, we are only going to focus on, if we are given 2 ketones, we're only going to focus on the interaction of one ketone against another. Typically, it will be a ketone against an aldehyde to ensure that we only have to consider one type of attack. And we're only going to work with one equivalent because you can quickly wander down the rabbit hole where, okay, you technically have 2 acidic groups. What's stopping it from like doing aldol condensation twice like it did for the lab? Yeah, I know that was a lot. It's very easy to overthink these problems. And I think you'll definitely, with the discussion board, you'll notice one group is a tert butyl. The tert butyl can attack. And because the tert butyl group can't attack, it pretty much guarantees only one there's only one alpha carbon on your attacking ketone. So there's only one possible product. So if you see something like this, this doesn't react. No reaction. And it ensures that we only get one reaction with itself because we only have one acidic carbon. Yes, it is incredible. This is the issue with these types of reactions. So it's like metathesis. I gave a talk, live stream on metathesis. I have videos of metathesis, and I say like self metathesis is a huge problem. So we write a simple metathesis problem, and it looks great. But then you consider, well, the product metathesis products can also undergo metathesis reactions with the starting reaction as well as each other, and so you don't end up with this simple like, oh, A goes to B. You have A goes to C, go to B goes to C, goes to D, go to E, and if you were to truly consider all the possibilities, you end up with this mess of products when you're done. Aldol condensations, again, that's why they're kind of getting their own test unit with a whole bunch of light stuff packed beside it. The aldol condensates, unless you really cook your answers, like we're going to do for the exam, or cook your questions like we're going to do for the exam, you can easily wander into super complicated space. So it feels like a lot, it is a lot, it's because it is. And I tried very hard to write the slides to kind of like, there's a reason why there's color coding with them. There's a reason why like I try to say, oh, this is, this is where this fragment came from. This is where this fragment comes from. Because even when I was writing these notes, it was a steep learning curve for me to figure this out. Like there is just a lot going on. Trying to do our best to kind of like help you out here, but yes, it is a lot. Right. I'm working on a presentation. I'm pretty sure you don't want to listen to me click through it. So I do have the chat open if you've got questions. All right, that's it for office hours. So again, if you have any questions, please feel free to ask in advance. Organic 1, I'm giving your test backs tomorrow, so I will see y'all tomorrow. Thanks for coming.